Hi, this is a problem on Webworks, and this is a topic about flexural stress, flexural bending stress. This is quite a challenging problem, and it is actually quite a realistic problem also. So let's spend some time to go over this. Um, so they said that this wooden deck is supported by the haystack, and there are four joists you see right here, right? There are four of them. They are spaced between with an interval of 2 A's, the spacing between them. And this joist is made of dry Douglas fir lumber, and they give us the width W. They also said this haystack is made by the square bale, and the square bale if you buy, and it's gonna weigh that much, and this is a dimension of the bale. And they assume the haystack, basically the roof here, has the same density as the bay, has the same density of the bale, okay? And then they give us the safety factor of 5 against yielding for this joist, okay? So then they ask you what is the value, maximum value of distributed load applied at one joist. Okay, so let's go through this logic together. First of all, they give us this bale. It's a square bale, and it's something like that. That's a bale. And they give us a dimension. Mine is 14 by 18 by 36. So that's the bale. And he said it weighs 68 pounds. If weighs 60 pounds, in other words, the mass is going to be 60 pound also, right? 6 pound mass, because 1 pound mass weighs 1 pound force. So what can we get from this information? First of all, we can find the volume of the bale. So it's going to be 14 times 18 times 36. That's going to give us an inch cube. Then we also know the mass. Then we can go ahead and find the bale density. The reason we do that, they said the roof density has the same density as the bale. So that's the reason why. So 60 pound mass over this volume of the bale. Then that's going to help us figure out the density, and that will give us the unit of pound mass per inch cube. That's the first step. Then using the density as a bridge, then we can figure out for this haystack. This haystack is in this shape. It's a triangular prism, and the dimension, this will be 2B, and this is C, and the length. There are 4 joists, and each one is 2A, so that will be 8A here. So we can figure out volume of the roof. So for triangular prism, and the formula is going to be 1/3 the area of the base, which is half base times height for that triangle, then times the height, 8A. So knowing that, we have our volume of this roof. So, but be aware, there are inch and foot for B and C, so it might be worse to change this B and C from foot to inches. If we do that, you are going to get the unit of inch cube right here for the volume of the roof. Now the third step, if you know this entire volume of this haystack or roof, then using the density you calculate in the first step, then you can go ahead and figure out the mass of the roof. That's going to be the density of the bale, same density as a roof, times the volume of the roof. And the unit should work out right because the bale is in pound mass inch cube, and roof is in inch cube, that's going to give the unit of pound mass right here. And then that will, from here, you can figure out the weight of this roof will be exactly the same value of the mass, but here is pound force. Okay, so that's what we have so far. We know how much does this roof weigh. That's the dead weight on those 4 joists. It's on 4 joists. So can we figure out on each joist how much roof weight is on? So that's going to be, we're going to say for each joist. Then we can figure out the weight of the roof for each joist. That's going to be half of this entire roof weight, right? Will be this value divided by 4. And that will give us the pound force. Okay, so now we're going to get some useful information. For each of those joists, we're looking at this view, and they will have this triangular distributed load onto it. Okay, that's how we approximate for each joist. And each joist has length of 2b, and the height is h right here, right? And the cross section is a rectangle, and the width is w, and the height is h. Then we need to figure out the first is what is the maximum value of this distributed load applied at one joist, which means it's right here. That's our peak. That's going to be our maximum value. That's what we're solving. That red point, that's summit. Now we're going to thinking about when we deal with distributed load, we equate or we approximate using the concentrated load. So if we were trying to find the equivalent of concentrated load for this triangular distributed load, we're going to figure out the area, right? The area underneath the curve is going to be the concentrated load. So the area is triangle, base is 2b, and the height is going to be your omega max you're solving. So here what you're solving is basically your equivalent concentrated load. So imagine all the loads, distributed load, are going to be just concentrated on one point, and how much is it? Will be half base times height. And that should be equal to this entire load on this one joist. And we already figured out, it's right here. The entire weight on this one joist is the entire roof weight distributed by 4 joists. So that's from step 4. So we know that. Then from here, we can go ahead and solve our maximum distributed load. Here, since this is pound force, here if you are going to use B in foot, you're going to get a unit, when you solve it, you're going to get unit of pound force per foot. Or potentially you could using this in inch also, right? In inch also, then you will get the unit of how many pound force per inch. And either one will work. Okay, so far we finished the first one. Okay, so it's not that actually straightforward to figure out the first problem, isn't it? You know, you have to start with this bell and then using the same density and then figure out the volume for this triangular prism, and then we can figure out the entire roof weight, then divided by 4 for each joist weight, and then we're using equivalent concentrated load to figure out this distributed load density. Okay, so now let's move on to the second one, the maximum bending at one joist. Well, the maximum bending, you already know this is going to be in this approach, right? That's going to be the load. You have this particular configuration. And obviously, we're going to have, it's a simply supported beam. You can find reaction. Those two should be the same. So ideally, you can go ahead and use those shared bending diagram. And then in that bending diagram, you're going to find your maximum bending. And so you can use graphical approach or analytical approach to figure it out. But here I'm going to start to introduce you something new. Once you're starting practice this as a structural engineer, if that's what you do for your career, they no longer go ahead and do those load share bending diagram, because those are common configuration. They already have a table set up for it. But if you have an uncommon external load, yes, you're going to use load share bending diagram to find the exact maximum bending. But for those, this is actually quite common. So I'm going to open up this one here. So this is from American Wood Council, American Wood Council, and they are using this national design specification for beam design. And here, if you look at the table of contents, have simply supported beam, they have cantilever beam, and etc. And they have a different distributed load. Let's just go scroll down. You have uniform distributed load. You can find a maximum bending here. They give you those information too. So in that case, we can just use that. That's where we are. And hopefully you get the same share and the same bending. So what we're interested in is this maximum bending. We know it happens at center. It's going to be this value. It's going to be omega L over 6. Okay, it's going to be this value right here. So, and this W is basically your maximum distributed load density, where you just found out. So, W, it's going to be WL times 6. Okay. Let me just double confirm if this W is right. Let me see, this W for R, here they have half of W. Okay, so this W is actually not your distributed load. Let me see what they have for this W here. That's omega A. Okay. Oh, okay. It's total uniform node. Okay. So it's not our omega. It's total uniform node. And we know that total uniform node, it's going to be the roof over one joist, right? Or the roof width over one joist. Okay. So now we know. I'm glad we stopped for a moment to figure that out. So it's omega, it's WL over 6. So knowing that, we're going to come back here. So this is going to be equal to WL over 6. And make a note, this W is the total load on the beam. Total load on the beam is going to be equal to what? For this situation, it's going to be the entire roof load divided by 4 joist. That's going to be the total load on this one joist beam. Okay. So knowing that, we can solve this maximum bending. Okay. Then, just to confirm with the unit, because this roof, it's going to be in pound force, and then times L. So that's going to give you pound force, and L, this L is 2B, right? So L here is 2B. Then we will get the unit of pound foot, because B takes the unit of foot. And that's what we needed for maximum bending moment. So the unit does make sense. Now the next one. What is the required height of the joist? All right, so this is the joist cross section with width W and height is H. And we can go ahead and use our flexural bending stress formula. We talked about that formula. It's like selfish formula. It's mi over I, right? And that's going to be your maximum stress this Douglas fir lumber can take. So that's going to be your normal stress and allowable. And this allowable is going to be this yield strength over the safety factor. So we first needed to know this yield strength for Douglas fir is actually 6,400 psi. You need to use that information to solve this problem. And the safety factor is given. So for mine, safety factor is 5. Okay, it's quite large, so they're very conservative designing this. All right, so safety factor is 5. Then you can find your allowable stress right here. So the right-hand equation is known. Now let's look at the left-hand equation. M, that's going to be your maximum bending stress, which you just calculated in step 6. And your Y is going to be the neutral axis distance to the top edge or bottom edge, right? Because it's a symmetric, the top or bottom, because the top edge is going to have what? Compression, and the bottom is going to experience maximum tension, right? But they also have the same Y. Y here is going to be half H. And how about our I, moment of inertia? For rectangle, it's going to be what? 1/3 base times height cube. So knowing that, the only unknown for this equation will be just H. And you can go ahead and solve that H right here. So from this, you can go ahead and solve H using this flexural bending stress, because this allowable stress cannot exceed yield strength over safety factor. Then you basically design your joist. You said, okay, for this joist, I have to have a height. This is a minimum height of that, okay? So that's minimum required height for this joist you just designed. Okay, the next step, they ask you, what is the minimum required section modulus of the joist? Now let's take a look. Section modulus, we talked about in one of the previous video, is M, maximum bending stress, over section modulus. That's equal to this flexural bending stress. We already calculated its yield strength over safety factor. So we already also know what's the maximum stress. That's known, right, from step 6 right here. So knowing that, we can go ahead solve your section modulus. That's one way to solve, right? Also, you can use another definition of section modulus, because what we said, section modulus is basically your I over Y. Okay, so knowing that, then you will be able to, since you know the I and you know the Y, you can go ahead and solve S2. And a quick review for section modulus is going to have a unit of length to the power of 3. So if you are going to use maximum bending stress using pound-foot, if you had pound-foot, and this yield strength you get, since it's in PSI, so that's going to be in unit of PSI. So I will go ahead and change this maximum bending stress to pound-inch. So knowing that, in order here to get pound per square inch, then you will get your section modulus of what? In unit of inch cube. Okay, so that will take care of our unit. So it looks like a foot to inch is a must to solve this problem. All right, now you solve the section modulus. Then the rest is go ahead and look at the number choice, and I will leave up to you which means your lumber choice have to be have a section modulus greater than this S you calculated, than this minimum section modulus you calculated, because that's a minimum. Okay, so that's all for this video, and you just designed a joist. All right, okay, I'll see you next one. Bye.